I want to try a small experiment. Close your eyes and imagine you're holding two plastic objects. No price, no brand, no information about the material. Very quickly, before you even have time to consciously analyze it, you have already made a judgment. You know whether the object in your hand feels like a precision tool you can trust or like something disposable, temporary, made to be used briefly and then forgotten. How do you know? Your fingers are incredibly sensitive instruments of perception. They can detect tiny differences in texture, differences your eyes might not even notice. But here is the interesting part. How can two objects belong to the same broad family of materials, both called plastic, and yet one gives you a sense of solidity and control, while the other feels immediately cheap? Why does the word plastic today almost sound like an insult to quality? How can the same word describe something as ordinary as a disposal bag and at the same time materials used in high-precision applications from medical technology to aerospace? That is what we are going to explore today. Why the difference between cheap and expensive is not always found in the material itself, but in the way that material behaves. To understand how we got here, we need to go back to time when plastic didn't feel cheap. It sounded like a solution. The world had started to run into a very simple problem. Natural materials had limits. Take ivory, for example. It was rare, extremely expensive, and demand for it placed real pressure on the nature. And there is something here that does not appear on the object itself. The value of a material cannot be completely separated from the way it was obtained. So the problem was not only price or availability, it was also that invisible cost. When billiard ball manufacturers looked for a substitute, they were not simply looking for something cheaper. They were looking for a way to get shape, durability, and repeatability without depending on a rare natural material. One of the first important commercial plastics, celluloid, showed exactly that possibility. It wasn't seen as cheap, it was seen as impressive because it could take shape and imitate materials that had been rare or expensive, such as amber or tortoiseshell. It was not perfect, it had serious limitations, including flammability, but it changed the idea of what a material could do. Then, in 1907, came bakelite. It was one of the first fully synthetic polymers, and it became valuable in the electrical age because it was rigid, heat-resistant, and electrically insulating. Bakelite was not just trying to imitate an older material, it behaved in a way that suggested stability, stiffness, and technical usefulness. Our perception of plastic didn't change because its chemistry became bad. It changed because the way we encountered plastic in everyday life changed. With mass production techniques such as injection molding, plastics could take complex shapes quickly and at enormous scale. But the more they appeared around us as thin, light, hollow, short-use objects, the more our brains began to read them through that pattern. We were not only evaluating the material, we were recognizing a behavior we had seen again and again. Something that bends easily, sounds hollow, and gets replaced quickly. And when a material appears so often as temporary, it starts to seem less valuable before we even use it. But here we need an important clarification. Plastic is not one material. It is a huge family of materials. Just like metals. When we say metal, we can mean anything from aluminum foil to the steel of a bridge. The same is true here. The word describes a category, not one specific behavior. A polymer is made of long molecular chains. In some polymer families, changes in chain branching, density, or how tightly those chains pack together can strongly affect stiffness, flexibility, and feel. But that doesn't mean disordered means cheap and ordered means expensive. When you hold an object, you do not feel the molecular structure directly, you feel the chemistry after it has passed through thickness, geometry, surface, sound, and assembly. This is where things become more specific. In many products, designers use principles of sensory design to shape the experience of the hand. Think about wall thickness. The stiffness of an object does not depend only on the polymer. It also depends on its dimensions. A flexible material can give a much more solid impression if the object has more thickness, the right curves, or internal ribs. The chemistry didn't necessarily change. What changed was the way that chemistry was supported by shape. Often what we experience as quality does not come from a more advanced polymer. It also comes from the mechanics of the shape, whether the material bends where it should, resists where the hand expects resistance, and stays stable during use. If an object gives way at a point where we expected stability, the brain doesn't need to know the material to change its judgment. It reads that movement as lack of control. But there is something that works even faster: sound. When an object touches a table, when a cap closes, or when you press a button, the brain is not just hearing volume, it is hearing mass, emptiness, vibration, and assembly. That's why the same sound does not always mean the same thing. A crystal glass can leave a clean, ringing sound that lasts, and that may fit its identity. Objects that give us a more solid impression often have a more controlled response to sound and vibration. That can come from the material itself, from the geometry, from fillers, from multiple layers, or simply from better assembly. A cap, a button, or a closing mechanism doesn't only have to function, its movement also has to end cleanly. Have you ever noticed that solid, muted click in a cap or a button? It is not only the sound of contact, it is the sound of a system that does not allow too much unwanted vibration to continue. Viscoelastic damping is one of the ways vibration decreases over time. It doesn't stop mechanical energy instantly, it disperses it and makes the sound die out faster instead of continuing to rattle. That is why rattle matters so much. When you hear parts continuing to move or creak, your brain doesn't need to know exactly what is wrong. And then there's the surface itself. Why do glass and metal often gives us a stronger sense of material presence? One reason is the way they exchange heat with the hand. Metal does this very strongly. Glass does it less, but usually more than many plastics. This is not just about thermal conductivity. It also has to do with how quickly a material can exchange heat with the skin when we touch it, something that depends on conductivity, density, and heat capacity. That's why at first contact, glass and especially metal can feel colder than a plastic object, sitting in the same room at the same temperature. Most plastics transfer more slowly, so they often stay closer to the thermal sensation of the hand, and that can make them feel less cold, less rigid, or less serious, even when plastic is exactly the right material for the job. The brain is not measuring thermophysical properties, it is translating that first loss of heat into a material impression. But heat is only the first piece of information. The surface finish can completely change the first impression. A glossy surface may look impressive under light, but in the hand it can bring different information. Fingerprints, drag, small marks, or what we call stick slip. That feeling where the finger doesn't glide smoothly, but catches and releases across the surface. That doesn't mean glossy is cheap, it means the eye and the hand do not always read the same thing. By contrast, a controlled, matte surface with the right micro roughness can make the movement of the finger feel drier, calmer, and more controlled. Not because matte is always better, but because it changes friction, contact, and the way skin moves across the material. Sometimes what we call a premium feel is not the surface that looks the most impressive. It is a surface that behaves more predictably when you touch it. So the next time you hold a plastic and immediately feel that it seems cheap or more serious, do not stop at the word plastic. Read the signals. First, apply light pressure where your hand expects stability. If the object bends easily there, it may be a question of wall thickness, geometry, or reinforcement. Then listen to it. A sound that resonates lasts longer than expected, or feels hollow may point to low mass, hollow geometry, or weak damping. Often, it sounds shorter, steadier, more finished. Then notice whether something inside it keeps moving. A small rattle, a creak, or a loose contact between parts may point to tolerances, assembly, or wear. One of the quietest signals of quality is the absence of movement that should not be there. And finally, move the edge of your finger across the surface. If the motion catches, breaks, or leaves strong marks, the surface is telling your hand something different. Plastic is not the verdict of quality. Behavior is. I'm Chrxstos, and thank you for watching.